Here's my tutorial on the Chatelier's principal simulation. I'm on the many collisions tab, which it actually says in number 2, but I've expanded the box labeled energy view. This is the energy view, I think, right there. And so the discussion in paragraph 1 is that the energy ends up higher, the potential energy of the chemicals ends up higher than it started. And I know it says reaction coordinate here. That is really confusing, and I'm not even sure exactly what that means. Essentially, this is time. So time is going on to the right. So my chemicals have some amount of energy, and just for simple numbers, let's just pretend it was 5 energies. And I know energy is not a unit, but we'll just keep this really simple for the moment. And it has 5 energies. So you put energy in then, starting here, and you probably heat it up, goes up, up, up. The potential energy in the system of the chemicals goes up. And at the peak here, they start to react. They finally have enough energy to make this reaction actually happen and turn into A, B, and C. So energy comes out as this happens, and eventually it's done, and it settles in at a new energy here. So from the perspective of the chemicals, energy went in more than it came out. And if this is a 5, then maybe this is a 20. So then it's gained 15 energy thingies over the course of this energizing and reaction happening. Kind of story. So look at the bold words in paragraph 1. This then is an endothermic reaction, and the heat is written on the left. So we would write in heat over here. When we put in heat, the reaction should shift to the right. And we have had a discussion about this. If heat is over here, then it is in a sense a reactant. And if I put in more heat, that's giving the left side what it wants. And what the system will do is stop being in equilibrium. Notice the 2 arrows, it's in equilibrium, and it will shift to the right. And I have put the heat on the left side. So I'm going to put in 40 A's and 40 BCs. And of course, they have to shift to the right because it's not even at equilibrium. We have to get some of this stuff made because we started at 0. But also there's an activation energy that we have to give them. So for any 2 molecules here to react, they have to have this much energy. And so far, only one of them has managed because overall, we don't have much energy in there. So I'm going to raise the temperature by turning on this burner here. And notice the green line going up on the right. And there another one reacted. And as the line goes up, we should get more of them that are able to have the right amount of energy to react. And we're already at 9. Okay, this seems to have settled into 18, 19, 20 kind of range. And as I said, it just went up. Anyway, sort of kind of there. So my answer for number 2 is it made more products and it settled to equilibrium. So for 3, in this reaction, heat is essentially a reactant. Remember, we put it on the left. So if we put in heat, the reaction should produce more products. Try it. What happened? And if we put in even more heat, we should get more products. Okay, we're going to go to number 4, change to the second reaction. Now, this one is a little bit disappointing because I think they should have made it more obvious. At first, it kind of looks like those bottom lines are the same height. I think the right one is supposed to be lower. So on 4, we end up with slightly less energy in the molecules than when it started. That means that this is an exothermic reaction, although not by much. And the heat in the reaction is written on the right side of the arrow. So we're going to put it over here in our reaction. So put the heat on the correct side. And there you can see what I did for number 4. I'm going to put in 40 of each of these. And this time it started with the heat way above the activation energy, so this should start off pretty well on its own. The difference here is that while we do have a lot of energy in the system, so a lot of them have activation energy, putting heat into this system actually makes the reaction go back to the left. So having the activation energy makes the reaction go to the right, but the fact that there is so much energy contained in the box makes the reaction go to the left. If the heat is on the right, then it is a product, and if I remove some of that, then I should get more product. So let's cool this and see what happens. So I've adjusted the energy line here, and by cooling it, I've actually made very noticeably more product. So I'm going to start here. Less heat should go to the right is my prediction. And in fact, I did get the result of more products. And I'm going to kind of just skip ahead here. And we're going to pretend if you give it more heat, it goes left. So just mentally put that green line back up at the top, and we should get the reverse, right? If you do the reverse, you get the reverse. If you do the opposite, you get the opposite. So if we put the heat line back up top, I think it should go left, and then yes, it goes left, and I get more reactants. So I'm just going to discuss the answers here. Put in more of the product chemicals. It doesn't matter if you have an exothermic or endothermic reaction. If you give it more products on the right, it will shift to the left. Take away some products, take them away, it will shift to the right. Take away some reactants, what happens? It will shift to the left. What's the pattern? If we put in more chemicals, the system will shift to the other side. If we take away chemicals, the system shifts to the same side as the chemicals were on. So putting in chemicals makes one side stronger than the other for a moment. We've shown that an equilibrium system that's stressed with a change will shift toward the weak side and away from the strong side.